Hey, what's going on, guys? Let's do this problem right here. So we have problem A right here, B right here, C, D. So let's do them one by one. So first question is asking, when a person sings his or her vocal cords vibrate in a repetitive pattern that has same frequency as the note that is sung. If someone sings the note B flat, which has a frequency of 466 Hz, how much time does it take the person's vocal cords to vibrate through the one complete cycle? So they are asking for the period, and then what is the angular velocity, angular frequency of the chords. So we need to find out the G and the omega, and they have provided the frequency for 66 Hz. So from this one, we can directly say that period is equal to 1 over f. So it's easy to find 1 over f, and we simply have to direct substitution. So this is going to be 1 over 466, and that gives us 2.15 times 10 to the power of minus 3 second. And omega is going to be equal to 25f, and 25 times this frequency, that is 466 Hertz, and that gives us 2.93 times 10 to the power of 3 radians per second. So we have answered the A part. So let's go to the B part. When sound waves strike eardrum, this membrane vibrates with the same frequency as the sound. The highest pitch that typical women can hear has period of 50 microseconds. So we have a period, and what are the frequency and angular frequency of vibrating eardrum for this sound. So they are asking for f and the omega frequency and the angular frequency. So they have provided the period, that is 50 microsecond. You can also say 50 times 10 to the power of minus 6 second. And from this one we have to find the f. So we know that f is going to be equal to 1 over t, and that's going to give us 1 over 50 times 10 to the power of minus 6, and the value gives us, if I divide this one by this gives us 2.00 times 10 to the power of 4 Hertz. And this is the frequency. We have to find the omega right now. Omega is going to be equal to 25f. Since we have the frequency right here, so we can simply substitute that one right here and find the omega. This is going to be 25 times 2.00 times 10 to the power of 4 Hertz. And if I find the value, that gives us 2. That's 1.26 times 10 to the power of 5 radians per second. Let's do the C part. Let's use a different color. So C part. Okay, so we have when light having vibration with angular frequency ranging from 2.7 times 10 to the power of 15 radians per second, 4.7 times 10 to the power of 15 radians per second. So they have given omega for these two, and this is the range, and it stimulates the receptor cells and the perceiver will be okay. What are the limits of the period and frequency of the light? So they are asking for the period and the frequency. So if we calculate the period and frequency during this interval, that's going to be the interval. So we have to find period and the frequency, and they have given omega. Let's say omega 1, that is 2.7 times 10 to the power of 15 radians per second, and let's say omega 2 is equal to 4.7 10 to the power of 15 radians per second. We have to find the period. We can find the f because we know that omega is equal to 2 pi f. So therefore f is going to be equal to omega over 2 pi. So let's do this for omega 1. So let's say f1. If I want to find f1, that's going to be omega 1 over 2 pi. We know that omega 1 is 2.7 times 10 to the power of 50 divided by 2 pi. That gives us 4.3 times 10 to the power of 40 hertz. And this is f1. F2 is going to be omega 2 divided by 2 pi. We have omega 2 right here. 4.7 times 10 to the power of 15 divided by 2 pi, and that value gives us 1.3 times 10 to the power of minus 15. Actually that is 7 point, wait a minute, this is 7.5 times 10 to the power of 14 hertz. So this is the range. So the range of the frequency is going to be from, so range is from 4.3 times 10 to the power of 14 hertz to 7.5 times 10 to the power of 14 hertz. So this is going to be the range of the frequency. So let's see what is the range of the period. So to find this one, what I can do, I have to find the period. So this is going to be inverse. We know that t is equal to 1 over f. Therefore t1 is going to be equal to 1 over f1. And we know the f1, that is 4.3 times 10 to the power of 14 hertz. So this is going to be 1 over 4.3 times 10 to the power of 14 hertz. And that's going to give us 2.3 times 10 to the power of minus 15 second. So we have the period 1. Let's calculate period 2. T2 is equal to 1 over f2, and this is going to be equal to 1 over 7.5 times 10 to the power of 14 hertz, and that gives us 2. This one gives us 2.3 times this is actually 1.3 times 10 to the power of minus 15 second. 1.3 times 10 to the power of minus 15 second. So we have the value for this t and the other t, so we can, the range is going to be from here to here. So the range from t ranges from 2.3 times 10 to the power of minus 15 to 1.3 times 10 to the power of minus 15 second. So this is going to be the range for the period. Let's go for the D part. High frequency sound waves are used to probe with the interior body to detect small as tumors. The frequency has given right here. And what are the period and the angular frequency? So let's find this. That is D part, right? D part. So they are asking for the period means T, and the angular frequency, and they have provided the frequency, that is 5.0 megahertz. So this can be written as 5 times 10 to the power of 6 hertz. T is easy to find because it's going to be f is equal to 1 over t. So we simply have to plug this value. So this is going to be 5 times 10 to the power of 6 hertz, and that gives us 2.0 times 10 to the power of minus 7 second. So we are finding the period. Okay. So we are finding the period, and omega is equal to, so we have the period, omega is equal to 2 pi f. So we simply have to multiply this one by 2 pi. So 2 pi times 5 times 10 to the power of 6 hertz, and that gives us 3.1 times 10 to the power of 7 radians per second. And that is the final answer. I hope you guys liked this video. See you next time.